Mars dust isn't dirty. It's charged, and the thin air around it has no way to make it stop. That isn't a metaphor. Every dust grain tumbling across the Martian surface is rubbing against every other grain, trading electrical charge the way a wool sock trades electricity with a carpet. And because Mars has almost no air, there is nothing to bleed that charge away. The sky above you is filling with something invisible, something looking for a place to go. You're on minute 3 of a 20-minute walk. Your suit's forearm panel is reading temperature data, regulating heating elements, monitoring 4 redundant sensors. You can feel the faint scratch of dust hitting the visor. You can hear it, a dry, papery hiss against the faceplate. You don't hear the charge building. No warning tone, no indicator light. And that's not even the part that kills most people. The part that kills them is what they think they already fixed.
Here's what's actually happening in the air around you. Dust particles on Mars are so small and so light that storms can keep them suspended for weeks. While they float, they collide, constantly. Each collision forces one particle to hand off electrons to another, the same basic physics as shuffling across carpet and wool socks and then reaching for a metal door handle, the familiar snap. Except on Mars, the charge doesn't snap into your finger and make you flinch. It builds and builds and keeps building. On Earth, our thick atmosphere, roughly 150 times denser than Mars's, absorbs that charge passively. The air acts like a sponge, pulling electrical potential off every surface it touches, dissipating it harmlessly before it can reach a dangerous level. Mars has no such sponge. The atmosphere is so thin it can barely slow the charge down, let alone absorb it. The result? Electrical field strength inside a Martian dust devil can reach 20,000 volts per meter, strong enough to force the surrounding air to give up and let the charge jump. That jump is a spark, a silent, instantaneous release of stored electrical energy into whatever conductive surface is closest. Right now, the closest conductive surface is you.
The way the charge moves matters. It doesn't wait for a path through open space. It doesn't need one. It travels along surfaces, the outside of your suit, the seam between materials, the edge of a panel cover, looking for the fastest route to the nearest unshielded circuit. Modern microelectronics are extraordinarily sensitive to this kind of event. The components inside a temperature regulator or a communications chip are engineered at scales smaller than the width of a human hair. A single uncontrolled discharge crossing those structures doesn't damage them the way a power surge damages an older device. It doesn't slow the chip down or cause glitches. It burns a permanent bridge through the circuit. The component doesn't degrade, it stops. Not temporarily, permanently. No reset, no reboot. The chip is dead, and it will remain dead for the remainder of the mission. Now the chain of failures begins, and each one is worse than the one before it. The temperature regulation circuit goes first. The discharge hits the forearm panel, jumps to the processor controlling the suit's primary heating loop, and the circuit burns. Your suit's heating system is still running, but it's now running without feedback. It has no idea whether the temperature inside the suit is 18 degrees or 2 degrees. It defaults to its last confirmed setting. If that setting was warm, it stays warm. If that setting was cooling, it stays cooling. You don't feel this immediately. You feel comfortable. That's the problem. The suit is no longer responding to your body, it's repeating a command from 3 minutes ago. While that happens, the discharge doesn't stop at the temperature circuit. The spike travels further. Power regulation chips share a circuit board with sensor arrays, and the energy bleeds sideways through shared pathways. A second processor, the one monitoring your oxygen consumption rate, receives a partial discharge. It doesn't die cleanly. It enters a loop state, cycling through error conditions and resetting repeatedly, consuming power. Your suit's battery was designed for 4 hours. The cycling processor cuts that to 2. You are now using emergency power reserves without knowing it, and you have 11 minutes of your scheduled walk remaining. Your communication system has its own processor,
On Earth, that processor would be protected by a simple metal enclosure, a Faraday cage, which blocks outside electrical fields from reaching the components inside. Your suit has one. It was tested. But the discharge that hit your forearm panel traveled along the surface of your suit's outer layer first, accumulating additional charge from secondary dust contact along the way, before reaching the chassis of the comms unit and punching through the casing at a seam. The seam isn't a flaw in the design, it's a mechanical necessity. Every suit has seams. Every seam is a gap in the cage. The discharge finds the gap and uses it. Your comm system goes into standby mode. To the habitat team 400 meters away, you have simply stopped transmitting. They assume a routine interruption. They wait. The protocol says wait 3 minutes before attempting contact. The 3 minutes begins now. Inside the suit, you are still walking. You feel fine. The temperature hasn't shifted noticeably yet. The heating loop takes time to drift. But the battery counter you check every 2 minutes now shows 40 minutes of reserve capacity instead of 110. You don't know why. You toggle through system menus. The cycling processor is still resetting. Each cycle kicks out a small error flag, and your display is full of yellow indicators. You have no baseline for what normal yellow looks like. You received 6 weeks of training on this suit. You don't remember what 7 simultaneous yellow flags means. This is the point of no return. Not because you are going to die in the next 30 seconds, but because the chain of failures that started with a temperature circuit has now consumed your backup communications, degraded your battery by more than half, and left you reading a display you can't interpret with a suit that is passively drifting away from the thermal range your body requires. You are 11 minutes from the airlock on foot. The habitat team will begin search protocol in 2.5 minutes. The suit will begin alerting you to low battery in 8 minutes. Physics has already made the decision. You haven't caught up yet. Here's a number that should stop you cold. In a lab on Earth, researchers recreated the electrical conditions of a Martian dust storm inside a pressure chamber, lowering the air density to match Mars, suspending charged dust, and exposing standard solar panel hardware to the result. 90 seconds. That's how long it took the simulated discharge conditions to cut the panel's power output by more than half. Not temporarily, not partially. A permanent 50% reduction in the energy available to power everything that keeps you alive. 90 seconds is less than the time it takes to walk from one end of a school hallway to the other. And a solar panel is not a microchip. A solar panel is one of the most robust pieces of hardware on a Mars lander. If that's what happens to the robust hardware, the delicate electronics in your suit's regulator system don't last that long. The 100x factor matters here. On Earth, the electrical field required to make air spark, to force it to give up and let a discharge jump, is roughly 100 times higher than on Mars. Earth's thick air resists. Mars's thin air barely tries. This means charge levels that would be harmlessly low in a Saharan dust storm are already past the discharge point in a Martian dust gust. You don't need a full storm. You need a light wind and some sand. The threat level that would require a severe dust event on Earth is reached on Mars by the mildest activity in the sky. There is no such thing as a small dust encounter on Mars. The obvious answer, the one every engineer reaches for first, is to seal the electronics. Put them in a metal box, a proper Faraday cage, block the outside field from ever reaching the circuits. And the first part of that answer is completely correct. A properly designed, fully enclosed, grounded metal enclosure does block electrostatic discharge. That part of the physics is real, and it works. The problem is what happens outside the box. The discharge doesn't wait to get inside. It accumulates on the outer surface of the enclosure, builds along its edges, and when the field strength is high enough, it arcs across the outside of the case and into whatever unshielded connection point it finds. A power cable junction, a data port, the edge of a battery terminal, the point where a wire exits the shielded housing and becomes exposed for even 2 centimeters before connecting to the next sealed unit. Every Mars suit and rover is full of those 2-centimeter gaps. They are unavoidable. The cables have to exit somewhere.
The sensors have to connect somewhere. The power has to flow in somewhere. Every exit point is a potential discharge path. Sealing the processor doesn't seal the wire leading to it. There is a second problem with sealing. Charging happens on the surface of the enclosure. The metal box collects charge just as efficiently as any other conductor. A properly designed Faraday cage also needs to be grounded, electrically connected to a reference point that bleeds the surface charge away before it builds to discharge levels. On Earth, grounding means a wire to the ground beneath your feet. The planet absorbs it. On Mars, the ground is insulating regolith, fine, dry, non-conductive dust that doesn't absorb charge. It accumulates it. Grounding a suit to the Martian surface doesn't dissipate the charge. It connects your suit to the same charge reservoir the dust particles are building from. The solution you reach for makes the problem worse. You built the perfect shield for the wrong threat. In November 2025, a paper published in Nature changed the engineering calculations for every crewed Mars mission on the planning board. The source was Perseverance, specifically its SuperCam microphone, an instrument originally designed to record the acoustic properties of rocks being vaporized by a laser. Researchers reviewing the audio data from dust devil encounters at Jezero Crater heard something that wasn't rock. They heard pops. Discrete, sharp, repeating acoustic events that matched the sound signature of electrostatic discharges. The same kind of snap you hear when you pull a static-charged sweater over your head, scaled up and occurring inside a column of charged dust moving across the crater floor. 35 additional discharge events were recorded during separate stormfront passages, each one confirmed. The team cross-referenced the audio data against the rover's electromagnetic sensors and found the two datasets matched. The pops and the electrical spikes were the same events. This was not theoretical modeling. This was not lab simulation. This was a rover on Mars with instruments sensitive enough to hear the air conducting electricity, sitting inside the storm it was documenting. The engineering assumption before that paper was that Martian electrostatic discharge was a probable hazard, something to plan for, model, design around, without direct confirmation it occurred at scales that would damage hardware. After that paper, the assumption changed. The discharges were real, measurable, repeated, and occurring at field strengths consistent with the lab data showing permanent hardware damage in under 2 minutes. Perseverance survived because it was designed with broad electrical tolerances, isolated circuit architecture, and redundant systems. It was not specifically hardened for electrostatic discharge. It got lucky in the same way a car not designed for off-road use can survive one dirt road without failing. But that's not a design principle. That's variance. A crewed mission cannot run on variance. Here is the timeless problem underneath all of this, the one that will follow every Mars mission until someone solves it. Protecting equipment from physical contamination is something engineers have done for a century. Filters, seals, coatings, enclosures, the entire toolkit exists, is tested, and mostly works. Protecting that same equipment from the electrical behavior of the contamination is a different problem entirely, with a different toolkit. And Mars makes it orders of magnitude harder simply because it has almost no air. The thin atmosphere that makes Mars feel like a frontier, quieter, lower gravity, sunsets that go purple before the stars come out, is the same thin atmosphere that turns ordinary dust into an electrical weapon. The beauty and the threat are the same property. The same sky that will kill your suit's temperature regulator will also, eventually, be the thing the engineers finally learn to account for. They haven't yet. The people going to Mars first will learn it firsthand, the way all of the most important lessons in spaceflight have ever been learned. In the field, from a failure that didn't show up in any simulation, because the simulation was modeling the dust and not what the dust carries.